Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In the previous module we discussed gradient, which is one of the operations that we perform with the del operator that we introduced. In this module we will quickly look at divergence, curl and Laplacian. These are the additional operations that you perform more often than other operations, and they are quite important on their own and they have a physical meaning. Remember that the physical meaning of gradient is that it allows you to determine in which way the function is changing at its maximum. Okay, that applied for the concept of a scalar field. Okay, you don't have a definition of gradient for a vector field because at each point you don't have a scalar function but you have a vector function. But there are certain operations that you can perform with the vector fields which prove to be very important for our electromagnetic discussion. And the first operation that I am going to discuss is what is called as divergence operation. Okay. To give you the physical meaning of divergence, first of all, let us assume that I have some isolated point, okay, and then I place a certain charge here. Okay. Do not look at the other parts of this slide here or the picture here, I will come back to that one. That is just a mathematical description of what we are doing. So, you have a charge placed here, and you know that if I were to place a small test charge and measure the electric field that is coming out of this particular charge, I know that this would be directed in this radial direction with the magnitude decaying as you move away from the charge, but nevertheless the electric field will be directed radially outward. So, you might even write that the way in which this the field can be written as some electric field E, okay, as a function of the radial distance r, where the radial distance r will be this distance. Okay, so this is the radial distance r, and then the direction of this can be written as r hat being the direction of the radially increasing vector. So this is how you can actually write down the vector field, and this is of course an example of a electric field vector around a positive charge, right. Now imagine that I take a small balloon or something and then try to cover this balloon or some kind of a box or this one that I will try to cover the charge. Okay, assume that the thickness of this box is immaterial, the box is empty, whatever, so it essentially is not disturbing. So what I am actually putting is just a virtual box kind of a thing, right. And if you are to observe just outside of the box, so let us say the inside of the box is not visible to you, if you were to just observe from the outside, then you will conclude that there must be a positive charge inside because you are seeing these lines coming out, right. You are measuring these lines and then you imagine that there is something of a positive charge that must be kept. A different way would be that if there is a tap, okay, so the water is coming out, or let us say the sprinkler that is present. So you have a sprinkler here, and if I cover the sprinkler with some unknown box, or if I cover that one so that I do not give you an access, but let you see the outside of the sprinkler and water is coming out of this sprinkler, right. So you will imagine, or you will tell me that surrounding this box must be some source of a water, which is why you are seeing some lines of water coming out. The sprinkler is sending you water. As you turn that one, the sprinkler is showing you the throwing out water in this way. If on the other hand I consider a black box and then see that there are lines which are going in, right, then I would immediately conclude that there must be a negative charge inside that black box, otherwise the lines would not have gone in. At the same time, if I consider a box and then there is a line something like this, so this is a surface, imagine that this is a closed surface, and you see that as many lines go in and as many lines come out, then your immediate assumption about the scenario or the guess about the scenario is that there is no source of charges inside, whether it is positive or negative, because if there was a source inside a positive charge, then there would have been some lines which are coming out. Okay. So to quantify this, so we are familiar with this phenomenon in which the lines are coming out or the sprinkler of the water is coming out. The physical picture of this is that of something that is diverging. You can even go back to physics classes or optics classes and imagine that a small convex lens, and if you send in light here, then the light that comes out, the rays that come out of that one will be all diverging from the lens. similarly you have something called as a concave lens, in which the lines actually start to converge into a particular point. That point is called as the focus point. So you are familiar with this concept of vergence. This could be a divergence or this could be a convergence. Mathematically you can associate a positive quantity to divergence and a negative quantity to convergence, and what you would have obtained is a very simple concept called as a divergence. Physically, divergence is all that is about. However, mathematically divergence is not defined as so simple as I have written down. Mathematically, the definition of divergence, suppose D is a vector field which will be changing at different points along the space. Mathematically, the definition of divergence is given by integral of this D over the closed surface, okay, divide this one by the volume of the closed surface. Okay, so you have imagined a closed surface. In the case of the charge, that was this closed surface, and there is a certain volume. So there is a closed surface S and a certain volume for this closed surface, which we label as delta V. And what happens if you start shrinking this volume, that is, you take the volume delta V and then take the limit of this volume delta V to 0, right? You make this, if you take the volume and then start shrinking this volume in more and more towards 0, and if you still see this quantity to be non-zero, right, so whatever the d of r that you are going to obtain dot ds, if that quantity is non-zero, then you say that this vector field D has a non-zero divergence, okay, and then you represent that one by writing this as divergence of D and defining this mathematically in this way, okay. So immediately you will be facing couple of questions. First of all, what is this integral that we have taken and how do I evaluate that integral? Turns out that this integral that we had in the previous example was supposed to be a closed integral. So let me go back and rewrite this one. This has to be a closed surface integral, okay. So what should be this closed surface integral and how do I evaluate it, okay. So that is the objective that I would just very quickly give you an idea of. Okay, so I know that this is a vector field D that I have here, okay, and this is the surface that I have picked. This surface is that of a cube, and as I know that the closed surface of a closed cube will have 6 surfaces, right. So it will be made out of 6 surfaces. There will be one front surface and there will be one back surface, then there will be one side surface to the right and there will be one side surface to the left, then there will be a surface on the top and surface on the bottom. What I have to do is to find out on this surface how does the vector field D behave, and then I have to take the dot product of this D at different points on the surface and then multiply that one by the infinitesimal surface area, okay. To make my concept or what I am saying little more clear, let me redraw that situation only with a front surface over here. Let us say my D vector is all going in this direction, okay. So D vector is in this particular direction, and then I have this surface over which I am trying to evaluate. Let us also consider the surface to be, so the center point to be made out of y naught and z naught, okay. This is at a constant x equal to x naught plus delta x by 2, okay. The reason for delta x by 2 is very clear. If you go back to this unit cube picture, the center of the cube will be having a point x naught, y naught and z naught, and the cube itself has a volume of delta x, delta y and delta z. Therefore, the front surface is actually given at x naught plus delta x by 2, the back surface will be given at x naught minus delta x by 2, okay, and the side surfaces will be given at some y equal to y naught plus delta y by 2, and the left surface will be given at y equal to y naught minus delta y by 2, and so on, okay. Focusing our attention only on the front surface, so I have to find out what is the value of this D vector at by fixing x equal to x naught plus delta x by 2 and allowing it to vary with respect to y and z in the limit of y naught minus delta y by 2 to y naught plus delta y by 2 and z naught minus delta z by 2 to z naught plus delta z by 2. So I have to find out, let us say I pick this particular point, okay. So I pick my infinitesimal area. That area will be given by dy and dz, at that particular point, and then I have to find out what is the value of the vector field D evaluated at x equal to x naught plus delta x by 2 and the corresponding value of y. Y goes over this limit, z goes over this limit, but over this small infinitesimal value I have to find out the exact value of y and z and then multiply that value of, or find out the value of d at that point, multiply it by dy dz, which gives me the infinitesimal area. Now here is a problem. This is a surface integral, okay, as we call it, but then there is a dot product sitting here. What does the dot product imply? Okay, let me erase this. This is not the definition, right? So what does the dot product do to us? The dot product means that I have to consider, okay, not any component of d, but only that component of d which is parallel to the infinitesimal surface area. For the surface area that we have considered, the corresponding vector element will be given by dy dz along x direction. So even though my d itself might have components as dx, dy and dz, not all three of them will be giving you a non-zero value if I find out the value of d dot ds over here. The corresponding component that I am interested will be only the dx component, because if I take the dot product of d with respect to this surface element dy dz x hat, only the dx component will come out. So what I have for the surface integral of d over ds over the front surface, in which y will be equal to y naught minus delta y by 2 to y naught plus delta y by 2, z naught minus delta z by 2 to z naught plus delta z by 2. The infinitesimal area, this integrand will actually be equal to dx evaluated at x naught plus delta x by 2 y and z multiplied by dy dz, because the vector area here ds is given by dy dz x hat, and the component of d that will give you non-zero value with respect to this integrand will be only the x component, and this x component is being evaluated at x naught plus delta x by 2. I also know how to do this one, right? I mean, if I consider what is dx as a Taylor series expansion, then I can write this as dx at x naught plus some delta x by 2, which is the small displacement from x naught that you are looking at, and then there is a partial derivative del dx by del x, right? This is applying Taylor series only to the first order and then integrating this one over dy dz with the appropriate limits. So I am not writing the limits again, but this is the way you would have to write down the appropriate limit. Okay, you can do this. This is what we have done is only for the front surface. You have to cover first of all this entire area by moving your delta x, delta y infinitesimal area around this limit, okay, and then once you have found this one out, you then have to put all these quantities together. For the front surface that you have obtained, you find that this is dx x naught dy dz, okay, and for the back surface, because the back surface is evaluated at x naught minus delta x, what you get is dx x naught minus delta x by 2 del dx by del x, okay, multiplied still by dy dz, and then you can remove some of them because some of these quantities will have to actually cancel with respect to each other. So when you put all these surfaces together, the front surface, the back surface and all of them, and combine them in order to evaluate the integral, you will obtain, you will have a delta x, delta y, delta z, that that gets cancelled by the delta x, delta y, delta z from the volume integral in the denominator, and eventually what you obtain is that the divergence of this vector field quantity to be given by del dx by del x plus del dy by del y plus del dz by del z, okay. Again I can use my del operator, okay, in order to write this equation slightly better in terms of a simplified notation. Consider what is this del dot d, okay. Remember that d is a vector field, which means that d is a function of x, y and z, and at every point you will have three components for d, that would be dx, dy and dz. And if I consider this operation del dot d, I know what is del, right? That is the operator x hat del by del x plus y hat del by del y plus z hat del by del z. So if I now take the dot product of this with respect to dx x hat plus dy y hat plus dz z hat, I clearly obtain the above expression. So divergence of d, which I have calculated, or rather I have just described how to go about finding that one out in the Cartesian coordinate system is actually given by del dot D. Therefore, when you write del dot D, you have actually obtained the divergence of D. Okay. So, this is the expression. Unfortunately, this expression of del dot D holds only in the Cartesian coordinate system. For the other coordinate systems, the expressions are painful to obtain, okay, but nevertheless you can obtain them. You can use the tables in order to find out what would be the corresponding expressions for divergence in the cylindrical and in the spherical coordinate system. Okay. So, this was all about divergence. The physical significance of divergence is that quantities which exhibit, or the fields which exhibit a phenomenon in which the field lines or the flux would be coming out. By the way, the flux is simply the closed value of the vector field quantity over the surface that you are considering. So, if you consider this one, this is actually the flux of D as we would call it. Okay. So, if you find that this quantity divided by delta V in the limit of delta V going to 0 happens to be a positive quantity, then you say that this is a divergent field. If it is a negative, then you say that the field has a negative divergence, and if this top quantity will be equal to 0, then you say that this quantity has no divergence. For example, consider the field quantity that would be uniform along some axis, right. So, you can imagine that there are these arrows which are all uniform along the entire space, and then imagine that there is a closed surface that we have made. Okay. So, you can actually imagine a closed surface, okay, in the form of a same thing that we had imagined, a cube, but instead of a cube you can imagine this any closed surface, and you would see that there will be as many lines as entering, as many lines as that would be leaving, indicating that this quantity, when you calculate the divergence of this one, will exhibit no divergence at all. So, this is a zero divergence field, but at the same time this quantity, whose amplitude is decreasing, as you can see as you move towards the right, okay, this actually has a non-zero divergence. This is slightly non-intuitive because divergence you normally assume it to be something like a rays coming out or rays that is going in, but you can also have a non-zero divergence for the case that we have considered here. Okay. So, this is all about divergence in the Cartesian coordinate system. You will immediately see when we talk of Maxwell's equations why divergence is very important. We move on to the next calculus bit that we are going to do with vector fields, and that quantity is called as a curl. Okay. Instead of developing the complete mathematical picture of that one, I will first give you the physical insight of a curl. Imagine that I have a surface. Imagine I am in front of a river. Okay. So, this is the river bed, and the water current will be strong at the surface and it would be weak as you keep going towards the center of the water surface, right. So, you imagine that you are moving in inside a submarine or something, and then measuring the water current. The water will be very fast in the surface, and as you go down the water current will be reasonably small, and then you imagine that there is a paddle wheel over here. So, I have a paddle wheel here, and what does the paddle wheel do now? I mean, if I imagine the paddle wheel out here, so I connect this one, there is a string with a paddle out there. You see that the current is stronger here, right, at the top, and the water current is weak at the bottom. So, the wings that are associated at the bottom will be pushed with larger force, okay, compared to the wings that are at the bottom. So, the effect of this one is that the paddle wheel will start to rotate. You can actually do this simple exercise by setting up a swirling whirlpool in your bathtub and actually placing a small paddle wheel out there. The paddle wheel actually starts rotating as the water speed is different at different points on the paddle. So, because it is rotating in one of the directions, if the water current is going in the other way, then the paddle wheel will rotate. So, you can actually associate a clockwise with some plus quantity and an anti-clockwise with respect to a minus quantity, but nevertheless this type of a vector field, right, wherein the quantity is causing a paddle wheel to rotate, is called as a curl, or this is called as a rotation field, and the quantity by which you rotate is called as the curl of that particular field. Okay. And mathematically the definition of curl is that I take the vector field. So, let us say that vector field happens to be H, and then I evaluate this H over the closed line integral. Okay. And after evaluating that one over the closed line integral, if I divide this one by the surface, that would be the open surface that I have. So imagine that this is the closed line integral or the contour that I am imagining, okay, and this is total area. The open surface will be the one which has a infinitesimal area of delta S, okay, and if I have a vector field that would be changing over, you know, over this particular loop in an arbitrary manner, then what I am trying to find out is the dot product of this vector field over the contour, right. So this numerator is what we call as a line integral. So this is a example of a line integral. You will actually see these integrals and other quantities in the textbook or in the problems that we are going to discuss, okay. And if you take the limit of this line integral, the closed line integral that you have considered over the contour that you have imagined, and then divide that one by the surface, that the open surface that the contour extends over, and then you take the limit of this delta S going to 0, that is you start shrinking and shrinking, and the result that you obtain is what is called as the curl of H, or sometimes denoted by rotation of H. So for this quantity to be non-zero, the line integral of this fellow should be non-zero. I won't give you the problems for line integral, I will leave that as exercises for you, or in the tutorial problems that I will give you, you can find how to solve these line integrals. But please remember, this is a closed line integral and this is delta S. Unfortunately for us, the expressions for this curl are not so simple, and in fact you can show that the curl of the field in terms of in the Cartesian coordinate systems can actually be given by this curl, you know, taking the del operator and taking the cross product of the del operator with respect to the with respect to the field H, okay. So this is your curl operation, this is a point operation, as does the divergence operations are. You now have, you know, you can find out the expressions for curl of H in different coordinate systems. As usual, this is little complicated in the spherical and the other cylindrical coordinate systems. It's not that it's very easy in the Cartesian, but you are able to find out the corresponding elements for this curl operation, okay. So far we have actually seen two operations, one is called as the curl and the other one is called as the divergence. Based on that, you actually have two kinds of a field, okay. One field where the divergence is 0, okay, whereas the curl of the field is non-zero, okay, and then you have the case where the divergence of the field is non-zero and the curl of the field is equal to 0. The field here in which the divergence is equal to 0 is representative of the charges, you know, or the electric fields that are coming out, and actually denote that there are sources of divergence out there. And if del dot D, the divergence, is equal to 0 and the curl is non-zero, then the field is called as solenoidal field, okay, because there is a rotation only and no divergence. And then you have other scenario where del dot D is non-zero but del cross D is equal to 0, then this is called as irrotational field, that is there is no rotation to this particular field, that paddle wheel that you put in will not rotate, okay. You will soon see that magnetic fields are usually the ones which have no divergence, that is del dot D equal to 0, but they will have non-zero curl, so that is they are the solenoidal fields, whereas the D vector, the electric flux density vector, usually has divergence but not rotational. Of course, you can also have a scenario where both divergence and curl of a vector field are 0, okay. Finally, I would like to talk about what is called as a Laplacian, okay. Laplacian is something that I will be using to develop wave equation, and therefore I will just very quickly talk to you about what is that. So I already know what is curl of H. If I am given what is the value of H, then by looking at certain of the expressions I can find out what is this curl of H, okay. Now if I take the curl of this quantity itself, then there is a vector identity which you can prove, okay, but it is actually quite tedious to prove, but this would be the vector identity, okay. This operation you already know, so this is the divergence operation, so this is divergence of H, and this operation, after taking the divergence you are taking the gradient, right. So you take the gradient of divergence of H minus, we do not know what is this operation, so we give a name to this as Laplacian, okay. So I have a name called Laplacian, and in terms of del operation, Laplacian is actually given by the dot product of del with respect to itself, okay. For the Cartesian coordinate system, this is very simple, this becomes del square by del x square plus del square by del y square plus del square by del z square. Okay. So you can apply this del square onto a vector, or you can apply this del square onto a scalar. The meaning of application of this del square or the Laplacian on vector is that you are applying this onto each of the components and the result will be a vector. Okay. So observe that del square goes onto hx and x hat, del square goes onto hy and y hat, plus del square goes onto hz and there is a z hat out there. Whereas when you apply this one to a scalar quantity, you are only applying it to the function of f itself. Okay. This Laplacian will be very important, and this equation that we have written, curl of h being given by gradient of divergence minus Laplacian, will be the starting point for us to derive the expressions for wave equation. There are a couple of notes that I would like to mention to you so that you are careful when you apply curl operation, divergence or other things. Del is an operator. Okay, so del is a operator. This del can operate on a vector field, okay, to give you a divergence. The result is a scalar. So operates on a vector field, but then the result is a scalar. Okay, and then you have curl operating on h. The result is a vector field. Okay, and what you obtain is a curl. Okay, so you operate on a vector and then you obtain a curl. Okay, gradient is something that you will have to operate only on the scalar. Okay, but the result of this scalar will be a vector. Okay, so this is a legitimate operation. Del f dot del g is a legitimate operation, but del dot d, okay, del dot d is not allowed. Why is it not allowed? Because the result of del dot d will be a scalar, and I can't take a dot product of a scalar with a vector. So this is not a legal operation, whereas this is a legal operation. Similarly, this is also not a legal operation, because curl of h will give you a vector and you don't take the the gradient of a vector. So these are the things that you should be a little bit careful about when you operate on this. And there is a list of identities, the vector identities that are involved with respect to the del operator. You don't have to remember everything, but you will have to be able to recall some of the important ones, especially the one that we talked about in the context of Laplacian. Okay, you have to remember some of those. And for all the other expressions, you might look at the textbook. At the back of our textbook, John D. Cross Electromagnetics, we have expressions for divergence, curl, Laplacian in not only the Cartesian coordinate system, but also in all the other two coordinate systems, the spherical and the cylindrical coordinate system. We close this module by reminding you that we have actually looked at several aspects here, although I have not developed them completely in detail. I will leave that one to you to understand that, because the goal is to move to Maxwell's equations as fast as possible. The idea is that we have looked at a line integral, surface integral. We have not looked at, but it's very easy to understand, a volume integral. Okay, associated with the surface integral, closed surface and dividing it by the volume gave us the divergence, which is the point operation. At a particular point you can find out what is the divergence of a vector field, and similarly you had a line integral divided by the surface, open surface of that one, and then taking the limit of the surface going to 0 gave you the curl operation, again which was a point operation. Okay, so these, and gradient of course we have already talked about in the previous module. So these operations will be freely used when we talk of Maxwell's equations. In fact, we will express Maxwell's equations in these operator calculus terms, and therefore you should study them before moving on to the next module thoroughly, so that you understand what divergence, curl, gradient, Laplacian, all these mean. So thank you very much.